So first of all, we will discover what is radio astronomy. So radio astronomy is a branch of astrophysics that studies celestial objects using radio waves instead of visible light. It allows astronomers to observe regions of space hidden by dust clouds and gas, such as nebula and more. The field began in the 1930s when Carl Jansky discovered radio emissions from the Milky Way galaxy. Unlike optical astronomy, radio astronomy can detect visible cosmic phenomena such as pulsar, quasars, and cosmic background radiation, or CBR. It expands our understanding of the universe beyond the visible spectrum.
We have the fundamental principles. In fundamental principles, radio waves are part of electromagnetic spectrum and have the longest wavelengths and lowest frequencies behind ultraviolet. Despite their low energy, radio waves are extremely useful in studying large cosmic structures. We have the two major types of radio emissions. For the first one, we have the thermal radiation, which produced by hot objects such as gas clouds and stars. And the other one, we have the non-thermal radiations, which produced when high-speed electrons move around magnetic fields. For example, we have the cyclotron radiations. Radio wave can pass through interstellar dust, allowing observation of hidden regions in galaxy. Earth's atmosphere is mostly transparent to radio wave, enabling ground-based observations, which we can see by the scientists use on the surface of the Earth to observe something is very distant from the Earth, like asteroids, stars, or planets like Venus, Saturn, or anything else.
Next, we're going to know how radio telescopes actually work and how they are put together. The first thing to know is that these things are built to detect incredibly weak radio signals coming from deep space. At the heart of the setup is that massive parabolic dish antenna, which is basically the giant bowl-shaped structure which we usually see. That dish collects those weak incoming radio waves and bounces them right onto a central receiver. From there, the receiver converts those signals into electrical data so we can actually analyze them. But because the signals are so weak, we have to run them through signals amplifiers to make them strong enough to read. This system actually have to be kept freezing cold. They use high-tech cooling system to keep the electronic noise to an absolute minimum, which makes the telescope way more sensitive to those quite cosmic whispers. So to wrap up this slide, the core ingredients we are talking about here are the parabolic dish, the receiver, the signal amplifier, and a powerful computer processing system to make sense of it all.
On my part, we have interferometry and telescope arrays. In this topic, we have the modern radio astronomy uses a technique called interferometry. So multiple radio telescope works together as one system, which signals from different telescopes are combined electronically. These techniques greatly improve image resolution, which are called very long baseline interferometry, VLBI. Telescope can be placed across different countries or continents, which creates a virtual telescope almost the size of Earth, which produce extremely detailed radio image of distant objects by seeing like planets of Saturn or Venus and other planets, which are distant for our perspective from
Resolution and sensitivity. Resolution is the ability of radio telescope to distinguish two nearby objects as separate houses. Higher resolution means astronomers can see finer detail in distant galaxies, nebula, and other astronomical objects. In radio astronomy, radio wave has much longer wavelength than visible light. Because of this, a single radio telescope generally has poorer resolution than optical telescope. Sensitivity. Sensitivity is the ability of a radio telescope to detect very weak radio signal from space. Many celestial objects emit extremely faint radio waves, so high sensitivity is essential for studying distant galaxy, pulsar, and interstellar gas cloud. Astronomers improve sensitivity by using longer observation time to collect more signal, using high-quality receiver with low electronic noise, reducing interference from Earth-based radio sources, and building larger collecting areas to capture more. Next, I would like to talk about key radio sources in the universe. First, pulsar are rapidly rotating neutron stars that emit radio waves in the regular pulses. These pulses are so precise that pulsars are often called cosmic clocks. Scientists use them to study gravity and the structure of the universe. Next, supernova remnants are the remains of exploded stars. They produce strong radio emission due to energetic particles moving through magnetic field. Studying them helps astronomers understand how stars evolve and enrich the universe with heavy elements. Quasars are extremely bright objects powered by supermassive black holes. They release huge amount of energy and can be observed from very great distance. Quasars have astronomers learn about early stage of universe. Lastly, cosmic microwave background is a faint radiation left over from the Big Bang. It fills the entire universe and provides important evidence about how the universe began.
There are several applications and contributions for radio astronomy, which is for mapping galaxies, because radio astronomy helps map to the structure of galaxies and spiral arms. This radio astronomy also can detect the black hole existence, which can detect the radio emissions near supermassive black holes. And radio astrology also used in cosmology, which helps scientists study the formation and evolution of the universe. And last but not least, radio astronomy also can be used in extreme physics for the researchers to study matter under extreme temperature, gravity, and magnetic fields. Radio astronomy also has transformed modern astrophysics and space science.
Now, let's talk about some of our biggest challenges and where the field is heading next. First up, the biggest challenges for astronomers is radio frequency interference, or RFI. Basically, our modern world is incredibly loud. Things we use every single day, such as smartphones, satellites, and broadcasting systems, these things will emit signals that can easily drown out the faint cosmic waves we are trying to listen to. It's like trying to hear a whisper in the middle of a rock concert. On top of that, we have a massive data problem. This telescope generates absolutely massive amounts of raw data every single second. Processing all of that requires some of the most powerful supercomputers and advanced software on the planet. But the future is looking incredibly bright. The project everyone is talking about right now is the Square Kilometer Array, or SKA. It is said to be one of the largest radio telescopes ever built. Once it is fully up and running, it's going to give us way better sensitivity and resolution than anything we have today. Honestly, it is expected to completely change the game and rewrite what we know about the universe.
In conclusion, radio astronomy allows scientists to observe visible, invisible regions of the universe. It has contributed greatly to discoveries involving pulsars, quasars, black holes, and the Big Bang. And these technologies such as interferometry continue improving observation quality. For future developments like the SKA project will lead to even more discoveries. Radio astronomy remains one of the most important tools in modern astrophysics as we know it.
Thank you for watching our video and have a nice day.